talk is about the design and status of Tera-Hertz FEL at Ariel by Aharon and Aharon.
Hi, everybody. First, I want to make a comment. This is the first lecture I give in Israel in 30 years. I see a lot of familiar faces. I'm disappointed in one thing is nobody actually stayed young here. So I expect in the next FEL, a plasma conference, something like a title, the use of plasma waves for for slowdown of the time flow, something like that. So let me see, how do I move here? Here we go. Before I start, there's something that I always hear is like people say, well, we can use a gyrotron to do millimeter waves or Tera-Hertz, and we can get much better results. And the answer to that is, yes, we can get much better results, but we actually are getting different results. For instance, if we look at what Harry was talking about, 2 talks before me, yes, you can get more power in 95 gigahertz from a gyrotron, and we know that, but you can't get the coherence that you get with a gyrotron. In this particular case, and I also have to start with an apology. I prepared a presentation yesterday, and as soon as I saved it on disk, my computer died. So I had to run home, and I have backups at home. The only problem was that the last backup was from the day before. So all the materials from the last day is lost. Well, it's not lost. It's hidden in a computer that doesn't work. Okay, so somewhat here there should be a pointer. Anybody can tell me? Oh, here. Oh, that's a nice pointer. Basically, the FEL that we're building, it's funded in part by Mafat. It's a collaboration with the physics department at UCLA. They are building the acceleration part, and we are building the free electron laser interaction part, and of course the detection. How does that work? It says here UV laser. We're using a photocathode emission. Obviously, you need to go above the red for magnesium or copper. So you shine the photocathode with a laser. In this particular gun, as I will show later, is actually unique. It's not something that was built quite that way before. But anyway, the idea here is the cathode is sitting in the acceleration field. There is no gun. The gun is the whole accelerator. So you accelerate the field. The idea here that you create a pulse. You give the pulse an energy chirp. As it accelerates, the pulse compresses, gets down to a very small length, and when it gets into the interaction field, an undulator, as Harry explained, you're talking about the pulse length that is much, much shorter than the wavelengths of the radiation. And so what you get is superradiance, where the radiation power is proportional to the number of electrons square as opposed to number of electrons where it usually is. You go out, you have to separate the electrons, and then you have to detect a very small pulse of Tera-Hertz, which is not simple. A little about the parameters. We're talking about 100 pulses per second. This parameter is actually limited by the klystron that does the acceleration. These klystrons can do up to 360 pulses per second, but they're pretty old, so we don't dare go above 100. Because otherwise we're going to talk about a lot of cooling. We're talking about the klystron that generates 25 megahertz of radiation. Now, The electron pulse duration, here it says 130, but it's actually less than 100 femtoseconds. The radiation pulse duration is actually about 7 picoseconds. The charge for a single pulse operation, and I'll show you later, we actually have also a train of pulses operation. The charge is 300 picocoulomb, so you can already make the calculation. You got 300 picocoulombs over 100 femtosecond. That's quite a strong current. Radiation wavelengths, let me express it in terahertz. We're talking about 1 to about 5.5, 6 terahertz that will be able to tune hopefully continuously without opening the device. And the pulse power for a single pulse operation is 175 kilowatt. For a multi-mode operation, we're still doing the calculations for not for multi-pulse, for a bunch beam operation. We're going to be at least an order of magnitude more than that, if not 2 orders of magnitude. Okay, let me talk a little bit about the laser. So initially I told you, I wrote there it's an ultraviolet laser. It's not an ultraviolet laser. It's an 800 nanometer laser. It's actually infrared. But the idea is 2 things that happen here. This is actually a pretty decent laser. It can emit pulses up to 35 femtoseconds, 6 to 8 millijoule per pulse. So we're talking about 200 or more gigawatt per pulse, gigawatt in a pulse. It's a very decent and very expensive laser. It also synchronizes the klystron, which is very important because we're talking with such short time that we need to synchronize different elements. The way the klystron is synchronized is there is actually a circuit in the laser. I don't know how many of you are familiar with how you create a femtosecond laser, but you create it with a piezoelectric crystal that vibrates the mirrors. And so they take that frequency that vibrates the mirrors and they multiply it into the klystron. The klystron is actually an amplifier. So the laser creates the signal that feeds the klystron, and that's how they synchronize in time. It goes to a frequency tripler where you get up to 30% efficiency. We don't believe we can get that much of efficiency. And then, again, this is not yet fully decided, but 35 femtosecond is too short for us. So we need actually 6 to 10 picoseconds a pulse in order not to get too much space charge, and then we actually compress the pulse to a smaller pulse. So we either stretch it here or not compress it here that much. And then we go to the photocathode. Now I will just say, as a statement, they have tried. There was an incident in UCLA where they operated the photocathode and they forgot to put the frequency tripler. So the photocathode, instead of receiving a 260 nanometer signal, received an 800 nanometer signal, but much higher power, and they got a lot more current, which we're still. So this is something that we don't think that can get photo emission with photons that are much smaller than the work function, but we got it. So we're thinking about how is that generated. I have my opinions about it, but I haven't done the theory about it yet. The electron gun is actually composed of two components. It has a standing wave component and a traveling wave component. Basically, this is where most of the acceleration is done, and this is where a little bit of the acceleration is done. But then what's introduced is chirp, so we can compress the signal. Now I'm told that then to compress a signal, we have to create a dispersion section. I'm told that the chicane might not work, and we'll just have to let the electrons disperse and compress themselves in free space. Don't know yet what's the case. Now, this is a rendition of the gun. If you see, it says here that we are the Schlesinger Family Center for Compact Accelerators. So, from here to here is 60 centimeters. So that's a gun that can create up to 6.5 MeV, and it's 60 centimeters long. This is, of course, looks here a lot longer than what really is. This is just the cathode housing. But the cathode is actually here, in the field. This is the gun with a solenoid. We put the solenoid, again, we have a lot of space charge. So in order to maintain the beam so the beam doesn't explode, we put the solenoid, and the solenoid creates focusing fields. 3, okay. Okay, this is the field amplitude. This is the standing wave section. This is the traveling wave section. We're getting here 80 megavolt per meter. This is a very decent acceleration, and that's why we can get at such a short distance up to 6.5 MeV. Okay, now going into the radiation. I don't think I need to explain how radiation works with FEL. This is the field at the end of the radiation section. It's not calculated fine enough, but you can see that it actually resembles very much a Gaussian beam because the field is actually created in an overmoded waveguide. So the field actually has to have the shape of the electron beam rather than the shape of the waveguide. Now, what's missing is I have done a calculation of what's going on after the field comes out, and we saw that this particular beam, we actually, with Tera-Hertz, there's always a problem how you handle Tera-Hertz. It's an optical wave, and I used the optical method to calculate it, and we see that in 30 centimeters the beam doubles its radius, which is not bad. We can work with that. Okay, at the exit, of course, we bend the beam, go out to a detector. Now, a detector all by itself is a problem, and we have 2 detection methods that we're working on them. I don't have the time to go into it. One of them is going to use an electro-optical mechanism, and the other one is going to use a Josephson junction-based antennas. Of course, instrumentation control. Now, and here we're talking about the future. Of course, we're going to operate this at a single chipped electron pulse or at a modulated pulse with 10 to 30 periods. You create the modulation by modulating the laser that's hitting the photocathode. And when you modulate the laser, you get an intensity field that has bits in it. And because the photo emission is based on intensity, the electrons are coming out, the electron current is coming out modulated. This has actually been tried both in Brookhaven and in UCLA. We want, in the not so far future, to go to using infrared and use a gyrotron for the wiggler, so use an electromagnetic wiggler. And hopefully the Tera-Wiggler group is going to be able to supply that. And of course, like everybody else, we're dreaming about tabletop X-ray free electron laser. Okay, that's the end of the talk.
Thank you very much. Rami?
Can you briefly comment on any planned application for this year?
Well, the applications are far. Right now, we know for sure that there is a demand for cancer research with Tera-Hertz. There is a lot of cancer research going on with Tera-Hertz going on in France, and in fact, the use in hospitals for diagnostics. Turns out that cancer cells have a special interaction with Tera-Hertz radiation. They absorb and reflect it, and And so definitely it's already used in France for diagnostics instead of pathological results. Other than that, fast spectroscopy, we're talking here about very short pulses. So transient spectroscopy, of course there are military applications, and we are a user center.
Okay. We may hear some comparison to electron beams for these uses in the afternoon. Thank you very much.